Let's try calculating some values of an equilibrium constant. So here we have a reaction. You've already written its expression before. And three different sets of equilibrium concentrations. And let's take a look at how that works. First, let's write the expression. We've already done that. That's already in your notes. So we have ammonia squared over hydrogen cubed times nitrogen. In order to calculate the equilibrium constant, we just take these values at equilibrium, so we know that the concentrations aren't changing, and we plug them in. 0.157 squared over 0.763 cubed times 0.921. As you put this in your calculator, don't forget order of operations. You can't say 0.157 squared divided by 0.763 cubed times 0.921. This has to be, oops, wrong color. This has to be in parentheses for that to work. So let's see what happens when we calculate that. And we get 0.0602. Okay, we have no idea what that means, but it's a number. We'll deal with that. So try that for the next two concentrations. Hit pause, and when you're ready, hit play again. Okay, so were you able to calculate these? Here are the expressions, and hopefully you got the number. So what this should tell us is that there is one equilibrium expression, one equilibrium constant at a temperature, and lots, infinite number of equilibrium positions. So let me say this again. This is our equilibrium constant. It is constant at a specific temperature. The only thing that changes it is changing the temperature, and we're going to talk more about that later. I can have any concentration of ammonia as long as my hydrogen and nitrogen concentrations are such that the ratio is 0.0602, it is at equilibrium. Things don't have to be at equilibrium. You know, when you mix things together, a reaction happens. So that's not at equilibrium. But at equilibrium, when we don't see a reaction happening, at this particular temperature, we know the ratio of ammonia squared over hydrogen cubed times nitrogen is 0.0602. Let's take a look at a second equation. We have ammonia breaking down into hydrogen and nitrogen. So the first thing we're going to do is write the equilibrium expression. Hydrogen cubed times nitrogen over ammonia squared. We're starting off with products over reactants. So now, at this set of equilibrium conditions, let's see if we can calculate the equilibrium constant. First thing I do is I plug the numbers in. Ammonia is 0.157, nitrogen 0.921, hydrogen 0.763. Then I type all that in my calculator, paying attention to order of operations, and I get 16.6. Still have no idea what that number means, but we'll get to that later. Okay, pause the video and try this for the next two. Okay, so hopefully you've been able to figure out that all three of these are 16.6. The point is that the ratio of products over reactants for this equation at this temperature is always 16.6. Doesn't matter how much nitrogen and hydrogen I have, if it's in a ratio with ammonia that gives me a K equals 16.6, it's at equilibrium. So I gave you two equations with two equilibrium constants, and they kind of look related to each other. So let's compare them. Equation 1 and equation 2 are the reverse equations. Oops. So equation 1 is the reverse of equation 2. Let's see how their equilibrium expressions are related. The first one has ammonia squared over hydrogen cubed nitrogen. The second one has hydrogen cubed nitrogen over ammonia squared. The reverse reaction has an inverse 1 over equilibrium expression. Reverse the equations, inverse the equilibrium expressions. Now let's take a look at those mathematical constants, the numbers we calculated. 0.0602 and 16.6. Try it in your calculator. You'll see how they're related. 1 divided by 0.0602 is 16.6. They're the inverse of each other again. So for any pair of reactions, if reaction 2 is the reverse of the first reaction, K2 is the inverse of K1. That's going to be useful for us later when we start to really get into the calculations with these, because we'll see that if we can easily, in an experiment, find the equilibrium constant for one reaction, we can mathematically determine the equilibrium constant for the reverse reaction. We'll take a look at that probably in a couple of days. So now it's your chance to practice a few of these. Here I have the decomposition of N2O5. That's the one we saw at the very beginning. Try writing the equilibrium expression and calculating the equilibrium constant. Pause the video, and when you're ready, hit play again. Okay, so hopefully you've been able to write the equilibrium expression. If you got this far, now make sure you have the rest of it. If you still don't, pause it again and start when you're ready. So what I did is I took the NO2, 0.3690, to the fourth power times 0.0990 divided by 0.0010. I came up with 1.84. Actually, that should have two significant figures. Okay, so that's where it really should be. 3 significant figures, 1.84. We still have no idea what that means yet, but we'll get there. Okay, try this one and the next one, and when you're ready, hit play again. All right, so this is acetic acid breaking down into hydrogen and acetate ion. Here's my equilibrium expression. And then I just plug in my numbers. And it's a pretty small number. Were you surprised that you got something times 10 to the negative fifth? Well, let's take a look and see what happens when you get the next one. Oops. So here we had really small concentrations and a really small equilibrium constant, times 10 to the negative 31. Remember that for just a few minutes from now. Okay, let's try one last problem. This one's a little tougher. Try it, see what you come up with. I'll give you some hints along the way if you need them. Okay, so let's take a look at some hints. Were you able to find the equilibrium expression? Now, it tells us the amount of ammonia is 0.75 molar. So I know what number I plug in there, but I have no idea what number to plug in there. Well, stoichiometry is our friend. We're starting with solid ammonium hydroxide, or hydrogen sulfide, sorry, which means there's no ammonia and no hydrogen sulfide. What a horribly stinky mixture. So, according to stoichiometry, if I make 0.75 moles of ammonia, and they're in a 1-to-1 ratio, I have to also be making 0.75 moles of hydrogen sulfide. So now I have 0.75 moles of each. Now it's a pretty easy calculation. That one shows up on the AP test every once in a while. That's a toughie. All right, we're going to finish up today with what does the equilibrium constant mean? So here's my reaction. If K is in the 1 range, then we have about the same number of equal products and reactants. So the reactions we looked at before, the one where we ended up with 1.86, 0.06, or 0.62, about equal. If K is 10, you have a little more product than reactant. Even if K is 100, little more product than reactant, but a lot of both. If K is 0.1 or 0.01, little more reactant than product, but a lot of both. If K is huge, we say that there's a whole lot more product than reactant. That's what we call a reaction going to completion. Those are the types of reactions you were limited to in first-year chemistry. Precipitation reactions have really huge equilibrium constants. And if K is super tiny, we have mostly reactant. That's no reaction. So that one we looked at with chromium hydroxide, one of the solubility rules you know is that chromium hydroxide does not dissolve in water. Well, that was a sort of lie. Tiny bits of chromium and hydroxide dissolve in water, but so few ions that we say it's no reaction. So what we're going to continue to take a look at is looking at the mathematics of this, and by looking at the equilibrium constant, we know, does a reaction happen? Does a reaction happen a lot, or a little bit, or not at all? So when we take a look at this next time, we'll take a look at the mathematics in a little more detail. If you have any questions, make sure you ask me. See you later. Bye.